Welcome to homework.
Hydrochloric acid has a pKa 7.54, and we are given the initial concentration. Initial concentration is 0.115 molar. So, what would be the concentration of hydronium, chlorous ion, and also hypochlorous acid um, at the equilibrium, and also the pH at the equilibrium? So, first of all, I will just convert the molecular formula for hypochlorous acid to HA here to make things easier. So we have HA plus water, and then we will produce A minus, which corresponding to our chlorous ion over here, and also hydronium ion. So we can set the ice table. The initial concentration is 0.115, and we don't have any. And then we don't have any for A minus and also X3O plus. So the chain will be minus X plus X for both. And then we have 0.115 minus X, and then we have X and X. So the Ka will be corresponding to our hydronium concentration times the concentration of A minus over the concentration of HA. So it will essentially equals to H squared equals to 0.115 minus X. Okay, so this will be the Ka expression. Okay, but at the same time, we don't know the Ka, but we are given the pKa. pKa essentially is the relative log of Ka. So if you go on to find out Ka, you just need to take the base 10 to the power of negative pKa. So therefore, our Ka value will be equals to 10 to the negative 7.54. All right, so we are going to copy everything. So our Ka 10 to the minus 7.54 equals to X squared divided by 0.115 minus X. Okay, so we are going to determine the Ka first. So we have 10 to the power negative 7.54, and then we should be able to find that it's roughly around equals 2.88 times 10 to the power left 8 x squared and 0.115 minus x. As you can see that the Ka is very small. It's 2.8 times 10 to the left 5. Okay, so generally by rule of thumb, when K is roughly around the magnitude 10 to the negative 5, we can consider it's a really small Ka acid dissociation constant. Okay, so when we have a small Ka acid dissociation constant, which means that the ionization is very weak, and then we only have very tiny of the ionization going on, and most of the chemical species is going to stay as HA for this case. Okay, so because only small amount of HA is going to dissociate, so the dissociation, the X value, the amount when compared to the initial concentration, will be really very small. So in other words, because the K is small, so the amount of dissociation is small, so X should be very small value. And when X compared to our initial concentration 0.0115, because X is very small. So when 0.115 minus X, you will approximate need equals to 0.115 because X is very small. So when you subtract a very small number, the actual value doesn't change at all. So therefore, from here we can make an approximation that the X is very small. So 0.115 minus X will be roughly equals to 0.115. So we already simplified the correlation over here. So we are going to solve for this equation to find X. And then if you solve for X, you should be able to find that X equals to 5.75 times 10 to the negative 5 molar. So it's a really small number. And when you go back to our equation, we should be able to find that, okay, so X essentially equals to the concentration of ClO minus and also hydronium. So this concentration essentially equals to ClO minus and also hydronium. Okay, so how about our concentration of our acid? So we just take 0.115 minus our X, and you should be able to find that the value is very, very small. So it's roughly around 0.115 molar for our acid. Okay, so how about for the pH value? So the pH value, we just need to take a negative log of the hydronium concentration, which will be 5.75 times 10 to the power of 5. And then we take a log of it and take a negative value. And then we should be able to find that the pH equals to 4.24. We take a negative log of 5.75 times 10 to the negative 5. So we will have our HA, HCl solved and also pH solved.